The next stop on our journey that is A to integration is a technique called integration by substitution. So imagine this. You're in the exam and you see this integral. You're thinking through what methods we've done so far. Yes, it's got e in it, but it's also got a fraction. There's no by parts because it's not one function times by another. Well, by making one of these substitutions, we can turn it into an integral that looks like this, which is a lot friendlier. So our goal with the substitution is to turn it into what I like to call a happy face integral, something that we know how to do and that we've seen many times before. So to the method then. Imagine you had an integral like this. We can't use by parts because whatever you make u and whatever you make v dash, when you minus the integral of u dash v, it will be more complicated and we won't be able to solve it. So instead we have to use a substitution. You'll see in a future video we could actually use the reverse chain rule, but we'll do a substitution for today to showcase the method. Very often we let the substitution letter be u. It's not always u, but it's quite a common one. In fact, this method is sometimes called a u substitution. You won't always be given the substitution, but in this case I'll give it to you. U is equal to 1 plus cos x. See if you can work out what substitution I'm making and why, as I do more and more examples in this video. This integral is in terms of x. We want to make all the x's change into a different letter to give us our happy face integral. Well, the first thing we can do is see that u is 1 plus cos x. So this integral is the same as sine x square root u dx. Is that a happy face integral? Doesn't look like it to me. First thing is we've got a dx at the end with a u in the middle, and we've got a sine x at the front. Not very friendly. How are we going to get dx then? Well, it looks kind of like a derivative, so what we do is we take a derivative. du dx. Hopefully you know the derivative of cos x by now, minus sine of x. And just like you can do with the chain rule, you can treat this as a fraction. You can float this dx up to the other side like this. And moreover, you can then rearrange it to get dx is equal to, if we divide by this here, then we're going to get dx is equal to minus 1 over sine of x du. You can do du in the numerator, but I prefer to leave it at the end because you'll recognize it more as part of the integration if you do that. Let's make the substitution then. Sine of x square root u, and I'm going to replace the dx with minus 1 over sine of x du, like this. Do you notice that we can cancel stuff down? Swish, swish. Now that's gone. And now the integral will be minus root u du. And I'm pretty pleased with that. To integrate that, we first need to turn it into u to the power of a half. Then add 1 to the power and divide by the new power with the negative like that, plus c. Are we missing anything? Yes. If you go back to the original, it's all in terms of x, but our answer is only in terms of u. So what you have to do is you have to copy and paste the substitution that you made and pop it back into where u is. So u is 1 plus cos x. So what we can do is replace the u with 1 plus cos x. And now this will be our final answer. So to repeat the steps for the method, substitution, pop it in, differentiate and rearrange, pop the dx in, cancel out what you can, integrate the nice integral, and then don't forget to substitute it back in at the very end. There may be an extra step in the middle where you have to rearrange a bit more, but you would use the same substitution. Okie doke, another example. We're going to make a substitution. What do you think it's going to be this time? What are the options? Could be 2x minus 1. It could be the square root of 2x plus 1. It could be 2x plus 1. Maybe it's just 2x. The one that I'm going to go for is 2x plus 1. You'll generate a sense the more questions you do, but very often, if there's a square root or a bracket, it's what's underneath. Or if there's a weird power, then it's going to be what the power is. It's not always the rule. Again, try and generate a sense of what it may be. In this case, 2x plus 1 will work. You may find another substitution will work too. So this integral is going to be equal to, I'm going to make the substitution, 2x plus 1 is now u. So root 2x plus 1 is now root u. dx is there. We don't really want that, so let's differentiate and see what we get. du dx is going to be just 2. And if we times both sides by dx and then divide by 2, I'll do it all in one go. We're going to get dx is equal to 1/2 du. 2x minus 1 over root u times by 1/2 du. So we've got a du on the end, great. There's still an x in here. How are we going to deal with that? If we think about the substitution and we take away 2 from both sides, can you see that now we have 2x minus 1 in terms of u? That's exactly what we need to do. We need to replace all the x's with u's. So I'm going to take that, u minus 2 over root u times by 1/2 and then du. Doesn't look quite as pleasing as the last one, but this is a nicer integral, I swear. That's because we can now do, if we bring that half to the outside, u divided by root u is u to the power of 1 minus 1/2, so that's u to the power of 1/2, minus 2 lots of, it's root u but it's in the denominator, so u minus 1/2. So that could have been an AS integral. If you're not as confident rearranging that, make sure you cover your exponents again. This looks a bit friendlier to me. So what we're going to do, integrate it. So we're going to have a 1/2. I'm going to add 1 to the power and divide by the new power. Add 1 to the power, divide by the new power like that, which will give, so u to the power of 3 over 2 over 3, and then minus, that cancels out, 2u to the power of 1/2 plus c. And we're not done there because, again, the original integral is in terms of x. So what we need to do to finish off is write this as 1/3 lots of 2x plus 1 to the power minus 2 lots of 2x plus 1 to the power of 1/2 and then plus c. Now that's the final answer. If you don't believe me, you could always differentiate that if you really want to. So just to recap, in this one, the difference is sometimes you may need to rearrange some of the xy bits in order to get the u's. Whereas in the last one, the xy bit, the sin x, just cancelled out straight away. Sometimes it will cancel, sometimes it won't. Another example then. This time I put limits on it, so we'll have to think about what to do with them as well. There are 2 methods that you could do. Choose whichever one you prefer. We're going to make a substitution. What do you think the substitution will be in this case? I'm going to do 1 plus x squared. It's not in a square root, but it is technically a bracket to the power of minus 1. So again, you can use that. If it's in a bracket, that could be a nice idea for what the substitution could be if it's not given. Let's start replacing it then. So we can't do much with the 2x cubed yet, but we can replace this with u. dx at the end, not great. So let's start differentiating. So du dx is equal to, that's going to be 2x, times by dx on both sides, and then divide by 2x like this. So if I replace this, I'm going to get 2x cubed over u times by 1 over 2x du. Does anything cancel out? Yeah. So one of the x's and one of the powers, so I'm going to change that to a 2, cancel out. And so does the 2 and the 2. So we've now got the integral of x squared over u du. Still not perfect because it's in terms of x squared. So let's use our substitution up here. If 1 plus x squared is u, then what's x squared going to be? That's going to be u minus 1. Let's put that in. So it will be the integral of u minus 1 over u du, which will be the integral of 1 minus 1 over u du. That seems quite good. So at this stage, you'll notice I've not actually done anything with the limits. So it's up to you how you want to do it. Method 1 will be continue without thinking about the limits just yet. The integral of 1 minus 1 over u will be equal to u minus ln u plus c. And then if you remember our substitution, it was up here 1 plus x squared. So 1 plus x squared minus ln 1 plus x squared. And at this stage, what you could say is that means that the original integral, which was this, should be equal to what we've just found with the same limits, 0 to 1. You put in the 1, you put in the 0, and you subtract them away from each other. So in this case, what would we get? We'd get 1 plus 1 minus ln 2, subtract 1 plus 0 minus ln 1. So 2 minus 1 is 1, and then minus ln 2. ln 1 is just 0, so that will cancel out as well. That would be our final answer for the first method. So first method, integrate it, don't think about the limits, put the limits into the final x version at the very end. And the second thing you can do is up here, you can decide at which point you'd like to change your limits from x to u. I usually change it to u when I change it to du. And it's simply do the substitution. When x is equal to 0, what would be the value of u? Well, u is 1 plus x squared. So 1 plus 0 squared is 1. When x is equal to 1, u is equal to 1 plus 1 squared, which is 2. From here on out, I know it's a u integral, so I'm not going to bother writing u equals. And now at the end, I'm going to integrate to get u minus ln u from 1 to 2, which will be 2 minus ln 2 minus 1 minus ln 1, which is equal to 2 minus 1 is still 1, ln 1 is still 0. So you can see we get the same answer. Use whichever method works for you, change the limits and don't sub x back in at the end, or sub x back in at the end and don't bother changing the limits. So if that wasn't tricky enough, let's try this example. This example may feel hard because the substitution feels a bit backward. I'm going to let the substitution not be u equals, but be x equals this time. And I'm going to let x equal sine of u. This feels like a very strange substitution the first time you see it, but trust me, it will work. Very often you'll get this given, but not always. So let's see what we're going to get. 1 over the square root of 1 minus x is now sine u. So this will be sine squared u. Still dx. Let's change the dx. So dx by du, be careful which way around it is. Derivative of sine is cos. And this time to rearrange, do you notice he just times by the du? You don't need to divide by cos u. It's already on that side. So let's replace that. 1 minus, I'm going to do one more step down here. What's 1 minus sine squared? Hopefully you recognize that identity. That's cos squared. Times by dx is now cos u du. And let's keep going. What's the square root of the square of cos? Simply just cos. Times by cos du. I'll get my red pen out. Cross, cross. This is simply the integral of 1 du. You can ask for a happy integral. That will give us u plus c. But of course, the original is in terms of x, so we need to rearrange this for x. In this case, if we wanted u equals, we'd have to do the inverse. So we'd have to do sine to the minus 1 or arc sine of x if you've heard that. Both of those are fine. So the final integral will be sine to the minus 1 of x plus c. If you don't get given a substitution for this one, the idea is you are doing 1 minus x squared, and that is of the form of the trig identity. 1 minus sine squared is cos squared, and then you take the nice square root. So if you see something similar with a square under a square root, it's probably a trig substitution. Now I'm going to cycle all the way back to the start, and we'll do this example. Have a go at it yourself first, and then I'll walk through the solution. If you don't know what the substitution is going to be, I'll say that now. Now see if you can finish off the substitution, but in a few seconds I'll go right through it. Okay, we're going to integrate. We're going to do e to the 2x divided by 1 minus e to the x is u. That's dx. Don't like the look of it. So let's differentiate and see where we're going to get. In this case, we will need to times by dx and divide by e to the x, like this, which will give us e to the 2x divided by u times minus 1 over e to the x du. I'll change the limits in a second. I'm going to concentrate on the integral first. This will be, after a bit of cancellation, zoom, zoom, the integral of e to the x over u, but minus. We're still not happy because there's still an e to the x in there, so let's go back up to the original substitution and see if we can swap it out. So we want e to the x, so if we add e to the x to both sides, and then subtract u on both sides, that looks pretty good. And we're going to get minus 1 minus u over u du. Let's continue this. If we expand the bracket, we'll get u minus 1 over u du, which will be the integral of 1 minus 1 over u du. This is actually the same as the other substitution we made earlier on. So we should know how to integrate it. It should be u minus ln modulus of u. If you want to do the method where you don't change the limits, go for it now. I'm going to change the limits. So I'm going to go back up to the top, change to orange, and go x is ln of a third and x is ln of a half. When x is equal to ln of a third, then u will be 1 minus e to ln of a third. But we like e and ln being together because they cancel each other out. So this is 1 minus a third, which is 2/3. And similarly, when x is ln of a half, u is 1 minus e to that. Cancel out, nicely done. U is equal to 1 minus a half, which is a half. So at this stage here, I'm going to put u is equal to 2/3, and then at the top u is equal to a half, and then as I go further down I'm not going to bother putting the u equals because it says du at the end, so I'm going to assume it is. Do you notice that 2/3 is actually bigger than a half? That doesn't seem right. That's okay. If your limits change order, don't worry about it. Keep them with their corresponding x version. So when x was ln a half, u was a half, both at the top. When x was ln a third, u was 2/3, both at the bottom. Don't change the order unless you change something in the integral. Okay, now let's plug it in. 1/2 minus ln 1/2 minus 2/3 minus ln 2/3. 1/2 is 3/6 minus 4/6, which is minus 1/6. And then I'm going to do plus ln 2/3 minus ln of a half. Just change the order because it makes it a bit easier to divide them. So minus a 6 plus ln, this is going to be 2/3 divided by 1/2, which if you do a keep, flip, change, then that will turn into 4/3 as the final answer. And we're done. Well, there you have it, another integration technique done. Here are some hints and tips. See you in the next one.